Hey, how's it going? Welcome back. Today on Milanese Math, we're going to be talking about rates and ratios. And as always, if you want to follow along with the worksheet that we're using, you can find it at the first link in the description below. So rates and ratios are very similar. They kind of go together. Let's start by defining them. A ratio is how two numbers compare. Okay, so how two numbers compare. So if we're talking about the ratio of something, it's how those two numbers are going to relate or compare to each other. A rate is a ratio with two different units. So if we are talking about a ratio that has different units in the numerator and the denominator or in the comparison, then we would consider that to be a problem involving a rate. And there's all kinds of rates that pop up in real world problems. So that's sort of what we're going to be looking at today. So let's look at number one and talk about rates and ratios in context here. So it says a model car has a 24-to-1 ratio. That means that for every 1 unit in the model car, the real car is 24 times larger. And that's a pretty common ratio for model cars. So it says if the model car is 7 inches long, how long is the real car? So there's a couple ways that you could think about this. Sometimes when you think about a ratio 24-to-1, you could think of it as a fraction, 24/1. And this is kind of like saying for every 1 unit in the model, so this is the bottom, then the real car is actually 24 times as long as that. So one way we could solve this problem is just using some real basic algebra. And we could say that if we know that the model car, remember the model car is on the bottom in the denominator, if that happens to be 7 inches long, then how long is the real car? And so in algebra, we use variables or letters to represent an unknown, and a lot of times we use an X. So the thing that I don't know is how long that real car is. And if you remember from your maybe an algebra class or something like that, you can do some real basic cross multiplication to get the final answer here. So the way we cross multiply is we take the denominator from the first one times the numerator from the second one. So 1 times x is x equals, and then cross that up and multiply. So 24 times 7 is going to be 168. So the final answer is 168, but as always, don't forget to label your final answer, and in this case, it was inches. So if the model car is 7 inches, then the real thing is going to be 168 inches. Now, that's not the only way you could have gotten this as a final answer. There's more than one way to solve a problem, usually in a math class, but this is just a quick example of how ratios pop up in math classes. So let's take a look at another one, number 2. It says, in last night's game, Corey made 14 of 18 shots from the field. What is his ratio of made to missed baskets? Okay, so in other words, if we use the colon here to talk about the made to missed baskets, the first one I want to talk about is the made baskets. How many did he make? Well, he made 14. So how many did he miss? And don't say 18. That's the total number of shots that he took. 14 of them he made. That means he missed 4 shots. So he was shooting really well on that night. So his ratio of made to missed baskets would be 14-4. Now, just like in a fraction, sometimes it's helpful to reduce or simplify it. And so since a 2 evenly divides into both of those numbers, I could also say that his ratio was 7-2. So for every 7 baskets that he made, he missed 2 baskets. And 14-4, 7-2, those are the same value. Okay? So that's a little bit about ratios. Now let's look at this in context with a rate, a problem that is a ratio of numbers with different units. So it says Erica's commute to work is 28 miles, and it takes her 0.5 hours to get there. What is her average speed? Speed, at least in a math and science class, is one of like the most classic examples of a rate. Okay, so it's a rate of change of distance over time. And in fact, that's the formula for it. So if we're talking about speed, we can take the distance traveled divided by the amount of time that it took us to travel that far, and that'll give us our speed. And of course, that's what it's looking for here. So what was the distance? Well, she traveled 28 miles and she did that in 0.5 hours. So if we take 28 divided by 0.5, that's going to give us 56. That's good as a final answer, but you need to have a unit with it. And of course, this is miles per hour. So you could do it like this, miles per hour, or MPH, because that's a pretty common abbreviation for it. Real quick though, let me back up to number 2. You'll notice there wasn't any units on that final answer, like 7 to 2. That's because with ratios, it's okay if there's not necessarily a unit. It's just a ratio of 7 to 2. So that's, I guess, one exception to where you wouldn't actually need a unit on that. Okay, let's do one more, and then I'm going to leave you with a few to try on your own. So it says the name brand coffee comes in a 12-ounce bag for $14. The generic coffee comes in a 20-ounce bag for $16. And our question is, which coffee is the better value? So essentially, this is asking a rate problem. It's saying, what is the rate at which you would spend money for this type of coffee? In other words, which one is cheaper? Which one has a lower rate? Well, if I need to do this, then I'm just going to be taking a look at the dollars per ounce. I want to think about, like, what's that lower rate? So if I'm going to compare the dollars to the ounces for the name brand, that's $14 for 12 ounces of coffee. And if you divide that out, it's $1.17 per ounce. So I guess you could say per ounce. So $1.17 per ounce. Okay, that's for the name brand, but what about the generic coffee? You're only going to be paying $16, but you're going to get 20 ounces of coffee. And so if you divide this out, you're going to get, 0.80, so 80 cents per ounce. So it's tempting. We've done all the math. We've got everything labeled, and it's tempting to stop right there. But think about their original question. It says, which coffee is the better value? Well, in this case, the generic coffee is going to be the better value because it's only 80 cents an ounce compared to $1.17 an ounce. So that's just a classic example of a rate problem that might pop up in a math class. So I'm going to let you try the rest of these. Hopefully this video was helpful, and if it was, consider subscribing to the channel. And as always, thanks for watching, and we'll catch you next time.